Okay, in this video we prove a statement that says an upper bound on the number of cut vertices a graph could have. So in a previous video we saw this path graph P of n, it has n minus 2 cut vertices, and the thing is that this particular bound, it is going to be the maximum number of cut vertices for any graph of order n. Okay, so this particular thing n minus 2 is going to be the most cut vertices for any graph of order n. Okay, so we are going to prove this particular thing. Okay, if you consider any graph, then the graph is going to have at most n minus 2 cut vertices. Okay, you cannot have more than n minus 2 cut vertices. Okay, so before proving that, we need a theorem. So let's first prove this theorem. So this theorem reads as follows. Okay, if T is a spanning tree of a non-trivial connected graph G, then T has at least as many cut vertices as G. Okay, so any spanning tree of a connected graph has at least as many cut vertices as G. Okay, so let's go and prove this statement. Okay, so let T be a spanning tree of G, and let let's say V be a cut vertex in G. Okay, and suppose U and W are two vertices in the graph such that every UV path in G passes through V. Okay, and suppose that U and V are two vertices such that every UV path in G passes through G. Okay, then we can see that so since T is a spanning tree of G, we can see that every UV path in T must also go through B. Okay, so that says any cut vertex of graph G is also a cut vertex of the spanning tree T. Okay, so any cut vertex of G is also a cut vertex of graph of that spanning tree T. Okay, so that says T has at least as many cut vertices as G. Okay, so therefore T has at least as many cut vertices as G. Okay, and that's the proof for this statement. So we will use this statement to prove the upper bound. Okay, so the upper bound says, okay, any graph, okay, it is going to have at most n minus 2 cut vertices. Okay, so we will be using this statement. So this statement says if it is a spanning tree of a connected graph G, then T has at least as many cut vertices as G. Okay, so here we proved that one, T has at least as many cut vertices as G. Okay, so here the argument is somewhat simple anyway. Okay, so let's go and prove the statement that we are looking for. So this statement says if G is a non-trivial connected graph of order n, okay, then G has at most n minus 2 cut vertices. So this is going to be an upper bound on the number of cut vertices in any connected graph. Okay, so let's go and prove this statement. Okay, so let T be a spanning tree of G. So we know that any connected graph has a spanning tree. Okay, and let T be a spanning tree. Okay, so let T be a spanning tree of G. So we know, okay, any tree of order n has at least 2 leaves. Okay, so any tree of order n has at least 2 leaves. Okay, so these leaves are not cut vertices. If you delete a leaf vertex, then we can say that it won't disconnect the graph. Okay, so that says any tree of order n has at least 2 leaves. So it has, that particular tree, it has at least 2 vertices. Okay, two vertices that are not cut vertices. Okay, so any tree of order n has at least 2 leaves. So if you consider a tree, it has at least 2 vertices that are not cut vertices. And let's look into the spanning tree T. Okay, therefore the spanning tree T of G, okay, this one has at most n minus 2 cut vertices. So we started with a spanning tree of G. So G has n vertices and at least 2 of those vertices are leaf vertices. So leaf vertices, they are not cut vertices. Okay, so that says any spanning tree of T. So here we took the spanning tree T, so that is true for this tree as well. So therefore the spanning tree T of G has at most n minus 2 cut vertices. Okay, so by the previous theorem we know this thing, T has at least as many cut vertices as G. Okay, so just invoke that theorem. So by the previous theorem, G has no more than okay, so that says T has at least as many cut vertices as G. So G has no more than cut vertices as T. Okay, G has no more cut vertices than T. Okay. So by the previous theorem, G has no more cut vertices than T. Okay. So that says, so G2 has at most n minus 2 cut vertices. Okay, and that's what we want to prove, because then G has at most n minus 2 cut vertices. Okay, and that's the proof. Okay, so this particular statement, it says something about the number of cut vertices a graph could have. So it's an upper bound on the number of cut vertices, and this particular graph, okay, P of n, path graph on n vertices has n minus 2, exactly n minus 2 cut vertices. So this graph has the maximum. Okay.